Here's lesson 3, solving linear systems by elimination. In the previous 2 lessons, you learned about different methods for solving a linear system. You learned how to solve by graphing, and also using an algebraic method called substitution. In this lesson, you're going to learn another algebraic method to solve a linear system, and it's called elimination. Remember that solving a linear system means to find the values of the variables that satisfy all of the equations in the system. Graphically speaking, that means you'll want to find the ordered pair x, y where the lines intersect. I'll be taking you through 6 examples. So we've got 6 different linear systems here that we're going to be finding the solutions to. Each of those 6 linear systems could have one of 3 possible scenarios happen when we try and solve the system. If the lines are not parallel, meaning they have different slopes, the lines will intersect at one point, meaning we will get one solution for x and y. If the lines are parallel, meaning they have the same slope, they're either going to be parallel and distinct, meaning they're going to have no solutions, or they'll be parallel and coincident, meaning that they have an infinite number of solutions. Here are all the steps for how you would solve a linear system using elimination. I'll reference those steps as we go through our examples. Let's do our first example. We want to solve this linear system using the method of elimination. This linear system is made up of 2 linear equations. Step 1 when solving a system using elimination is to get rid of any fractions or decimals you see. And for these 2 equations, there are no fractions or decimals, so we can move on to step 2, which tells us we want the equations to be in the format where we have both variable terms on one side of the equation and the constant term on the other side. Now both of these equations are already in that format, so we can move on to the next step, which tells us we want one of the variables in both equations, so either the x variables in both equations or the y variables in both equations, we want their coefficients to have the exact same absolute value. It could be the same sign or opposite sign, but we want them to have the same absolute value. And if you notice in these 2 equations, the y terms have coefficients that are the same absolute value. The absolute value of both of them is 2. In equation 1, it's a positive 2. In equation 2, it's a negative 2. But for the purpose of elimination, that's perfect. So what I'm going to do is I'm going to rewrite these 2 equations stacked on top of each other with their like terms lined up. So I'll rewrite equation 1. And beneath it, I'm going to rewrite equation 2, making sure that the like terms are lined up in columns. So I have the x terms in a column here. I have the y terms in a column here. And I have the constant terms on the other side of the equal sign in a column as well. And the next step of elimination is actually to add or subtract the like terms in these equations to create a new equation that has one of these 2 variables eliminated. Now since the y terms have coefficients that are the same absolute value, it is going to be the y variable that gets eliminated. We just have to decide, should I add these 2 equations or subtract these 2 equations so that the y terms get eliminated. And when the signs of the coefficients are opposite, adding the 2 equations will eliminate the variable. Let me show you how that works. So like I said, we're going to be adding the like terms together in both of these 2 equations. So I'll add the x terms first. I will do 3x plus 5x, and that gives me 8x. I'll do 2y plus negative 2y. That's 0y, which means there are no y's left. It has been eliminated. And then I have 19 plus 5. That's 24. I have a new equation with only one variable x. We need to solve that equation for x by dividing both sides by 8. Those cancel, and I have x equals 24 over 8, which is 3. We've now solved for x. We can take that solution for x and plug it back into either of the original 2 equations. I'm going to sub it back into equation 1, but you could sub it into equation 2. We get the same answer for y. So there's equation 1. I'm going to replace x with 3 because that's what we solved for it to be equal to. And now I'm going to solve this new equation for y. 3 times 3 is 9. I'm going to subtract that to the other side. 19 minus 9 is 10. Divide the 2 over. 10 divided by 2 is 5. So my solution to this equation is x equals 3, y equals 5. And graphically speaking, if we were to graph those 2 linear equations would intersect at the point 3, 5. Now, we should always check our solution when solving a linear system. We need to make sure that these are the correct answers for x and y. They would be the correct answers if they satisfy both equations. So I'm going to do a left side, right side check in both equations. So I've just shrunk the work here off to the side to give myself some room to do a left side, right side check. Let's do it for equation 1 first. I'll do left side, right side setup. The left side of the equation was 3x plus 2y. The right side was 19. Let me check my solution, 3, 5. So I'll sub in 3 for x and 5 for y. I get 9 plus 10, which is 19. Left side equals right side. That verifies that the point 3, 5 is on equation 1. If I can verify that it's also on equation 2, that tells me that that in fact is the point where the lines intersect and it is the correct solution. So let me do a left side, right side check for equation 2. Equation 2 was 5x minus 2y on the left, and on the right, it was 5. Let's sub in the solution, which was 3, 5. So sub in 3 for x, 5 for y, and I get 15 minus 10, which is 5. Once again, left side and right side are equal. So that point, 3, 5, is on line 2 as well. Since the point is on both lines, that's where the lines intersect. This must be the correct solution. So that was a fairly straightforward example of elimination to start off with. The y variables already had coefficients that had the same absolute value, so that one was easy. As we move on here, we'll see what we have to do if the coefficients don't start off with having the same absolute value. Also, I kind of skipped over why are we allowed to just add these two equations. Algebraically, why does that make sense that we can just add the two equations together and we end up getting a solution as to where the lines intersect? If you stay tuned until the end of the lesson, I'll put a little part in there where I'll go through the algebraic reasoning as to why we are allowed to add the two equations together. Let's move on to our second example, part B. If we follow the same steps, step 1 tells us to get rid of any fractions or decimals. We don't have to worry about that for either of these equations. Step 2 tells us to get the equations in the proper format. We want x and y on one side, the constant term on the other. Both equations are already in that format. Step 3 is where we're going to have to do some work. We want either the x's or the y's in both equations to have coefficients that are the exact same absolute value. And when I look at these two equations, neither the x's or the y's have coefficients that are the same absolute value. So we'll have to do some multiplying to make them be that way. Notice that if I were to multiply the x in equation 1 by 2, then it would have the same coefficient as the x in equation number 2. But I can't just multiply the x in equation 1 by 2. Then equation 1 isn't balanced anymore. But what I could do is multiply the entire equation 1 by 2, and then that keeps the equation balanced, and then the x's will have the same coefficients. Let's see what I mean. So I'm going to multiply equation 1 by 2. So 2 times equation 1 would equal, now I have to, like I said, I have to multiply that entire equation 1 by 2. That means all of the terms on the left and all of the terms on the right. So I need to do 2 times x, which is 2x, plus 2 times 4y, which is 8y, equals 2 times 6, which is 12. Notice I multiplied every single term in equation 1 by 2. I'll leave equation 2 exactly as it is. Notice when I rewrote these equations, I stacked them on top of each other with like terms lined up in columns. And now I need to either add or subtract these equations to eliminate a variable. Since the x's have the exact same coefficient with the same sign, subtracting the equations will eliminate the x variable. When the coefficients have the same sign, we subtract. If they had opposite signs, we would add. But since the x's coefficients have the same sign, we will subtract the two equations. And when we subtract the like terms, 2x minus 2x, that's going to give me 0x. The x is eliminated. You could write 0x if you want, but you typically won't see me write that. Continue subtracting the like terms that are lined up in columns. We have 8y minus negative 3y. Be careful when subtracting a negative. 8 minus negative 3 is 11. So we have 11y equals, and then I have 12 minus 1, which is 11. 11 times y equals 11. Divide both sides by 11, we figure out y equals 1. Sub that solution for y back into either original equation. I'll sub it into equation number 1. And I'll sub it into the one before I had doubled it. Just makes the numbers a little smaller to work with, but it doesn't matter. We could sub it into either original or the one that had been doubled. You'd get the same answer for x in all three scenarios. So I'll rewrite equation 1. And now I'll sub my answer of y equals 1 into this equation and solve for x. 4 times 1 is 4. Subtract it to the other side. 6 minus 4 is 2. So my solution to this equation is x equals 2, y equals 1. You could write it as the ordered pair 2, 1, because graphically speaking, that is where the two lines would intersect. And once again, we could check our answer by subbing those answers for x and y back into both original equations, showing it satisfies both equations. So I just shrunk my work here so that I can check the solution x equals 2, y equals 1 in both equations to prove that that's where the lines intersect. So I've split equation 1 into left side, right side. I'm subbing my answer of 2 in for x, 1 in for y, and I see that left side equals right side in equation 1, so that point's on equation 1. Let me also prove that point is on line 2. I've split it into left side and right side of the equation. I'm now plugging my answer of 2 for x and 1 for y. I get 4 minus 3, which is 1. Once again, it satisfies equation number 2, so we have the correct answer, 2, 1. Let's move on to our third example. Once again, there are no fractions or decimals to worry about, and the equation's already in the proper format, with x and y on one side, the constant on the other. Our main focus here is going to be on getting either the x's or the y's to have coefficients that are the same absolute value. In the previous example, we only had to multiply one of the equations by an integer to make that work. But notice in this one, there's no integer value I can multiply 3 by to make it equal 4, and same with 2 to 5. So what I'm going to have to do is multiply both equations by a value to get their coefficients to be the same. So I think this time I'll make the x's have the same coefficient again. So I will look at their coefficients, 3 and 4, and I'll find a common multiple between the two. A common multiple between 3 and 4 could be the product of 3 and 4, which is 12. So in order to make the coefficient of the x in equation 1 be 12, I'd have to multiply it by 4. So I will multiply all of equation 1 by 4, which would give me 3x times 4, which is 12x, plus 2y times 4, which is 8y, equals 2 times 4, which is 8. Notice all three terms got multiplied by 4. And now I want the x in equation 2 to have a coefficient of 12 as well. Right now it's a 4x, so I'll need to multiply that by 3. So I'll multiply all of equation 2 by 3. 3 times 4x is 12x. 3 times 5y is 15y. And 3 times 12 is 36. I've rewritten the equations so that all the like terms are lined up in columns. And now I'm going to choose whether I'm going to add or subtract the like terms in these equations to try and eliminate the x variable. Since the coefficients of the x's have the same absolute value and the same sign, subtracting will eliminate the variable. So let's subtract all of the like terms in each column. 12x minus 12x is 0x, so the x is gone. 8y minus 15y is negative 7y. And 8 minus 36 is negative 28. I'll divide both sides by negative 7. Negative 28 divided by negative 7 gives me 4. I'll take my answer for y and sub it into either original equation. I'll sub it into equation 2 this time. So I've got 4x plus 5y equals 12. I'll replace y with 4 and solve for x. 5 times 4 is 20. Let me move it to the other side by subtracting it. I've got 4x equals negative 8. Divide both sides by 4. Negative 8 divided by 4 is negative 2. So my solution is x equals negative 2, y equals 4. Graphically speaking, these lines would intersect at the point negative 2, 4. And we could do a left side, right side check in both equations to verify this is the correct solution, using the same method I showed you in the previous two examples. But I'll skip that for this example. Let's move on to our fourth example. This is the first time where we'll have to pay special attention to the first two steps of how to solve a system using elimination. We have decimals that we'll want to get rid of, and also if you look at equation 2, it's not in the proper format. So I'm actually going to start by putting equation 2 in the proper format. So I'm going to rewrite equation 1 the way it is. It has x and y on the left, the constant term on the right. And equation 2, I'm going to want x and y to be on the left and move that constant term to the right. And I'm going to want the x's and the y's lined up underneath the x's and y's from equation 1. So I'm going to put the 0.7x first. Then I'm going to put the negative 0.4y. And then I'm taking that negative 2.9, moving it to the right. It becomes positive 2.9. Now I'm going to want to get rid of these decimals. Notice that all of the terms have a single decimal place. If I were to multiply both equations by 10, we would have only integer values left. There'd be no more decimals. So let's do that. I'm going to rewrite equation 1 beside itself, but I'm going to multiply it by 10. So that means I need to multiply all three terms in that equation by 10. So I'm going to get 6x minus 3y equals 24. And equation number 2, I'll also multiply by 10. And that would give me 7x minus 4y equals 29. Now that the first two steps are taken care of, we can go ahead and move on to step 3, where we're going to want to make the coefficients of either the x's or the y's have the same absolute value. Let's work with the y's this time. I see the coefficients are negative 3 and negative 4. Just like the last example, we know a common multiple between 3 and 4 is 12. So I'm going to make the coefficients of the y terms in both equations both be negative 12. So I'll need to multiply this new version of equation 1 by 4. And make sure you multiply every term in that equation by 4. So that would give me 24x minus 12y equals 96. And to make that negative 4y in equation 2 have a coefficient of negative 12, I would have to multiply it by 3. So I'll multiply the entire equation by 3. That gives me 21x minus 12y equals 87. And now I need to decide, would subtracting or adding these two equations eliminate the variable y? Since the coefficients have the same absolute value and once again the same sign, when they're the same sign, we subtract. So when I subtract the like terms in the columns, 24x minus 21x is going to give me 3x. Negative 12y subtract negative 12y is going to give me 0y. The y has been eliminated. And 96 minus 87 is 9. Divide the 3 over, x equals 9 over 3, which is 3. And I take that solution for x and sub it into either original equation. So let's sub x equals 3 into either original equation, equation 1 or equation 2. I'll sub it into equation number 1. So I've rewritten equation 1, and now I'm going to sub my answer for x into this. 0.6 times 3 is 1.8. I'm going to take this 2.4, bring it to the left, so it becomes negative 2.4. And I took that y term, I'm going to move it to the right, it becomes positive 0.3y. So I've got negative 0.6 equals 0.3y. Divide the coefficient of 0.3 to the other side. Negative 0.6 divided by 0.3 is negative 2. So my solution here is x equals 3, y equals negative 2. Graphically speaking, that means the two lines, if they were graphed, they would intersect at the point 3, negative 2. Another reminder, we could check this solution as long as you plugged it into both of the original equations, but I won't show that for this question either. Part E, we have some fractions. Let's start by getting rid of the fractions. So let's just look at equation 1. Notice the denominators are 2 and 8. If I multiply that equation by a common multiple between 2 and 8, that will get rid of the fractions. The lowest common multiple between 2 and 8 is 8. So I'm going to multiply equation 1 by 8. So I need to do 8 times x over 2 plus 8 times y over 8 equals 8 times 4. Right? All three terms in that equation have to be multiplied by 8 to keep it balanced. And when I do this multiplying, 8 over 2 is 4, so that term is going to be 4x. 8 over 8 is 1, so that's going to be 1y. And 8 times 4 is 32. So I'm going to rewrite this as 4x plus y equals 32. In equation number 2, the denominators are 3 and 2. The lowest common multiple between 3 and 2 is 6. So I'm going to multiply equation 2 by 6. So I'll have to do 6 multiplied by all three of the terms. And when I reduce these fractions, 6 over 3 is 2, so I get 2x. Minus 6 over 2 is 3, so 3y equals negative 12. So I'm going to rewrite this as 2x minus 3y equals negative 12. Notice these are in the proper format, where we have the x's lined up in a column, the y's lined up in a column, and the constants on the other side of the equal sign in a column. But neither the x's or the y's have coefficients that are the same absolute value. So we could eliminate the x's if I multiplied equation 2 by 2, that way they both have a coefficient of 4, but I think I'll eliminate the y's. I'm going to get the coefficient of the y in equation number 1. I'm going to make that coefficient be 3, so that it'll have the same absolute value of the y in equation number 2. So I'm going to multiply this equation by 3. And when I multiply all three terms in that equation by 3, I get 12x plus 3y equals 96. And equation 2, I'll just rewrite it the way it is, but I'll make sure the like terms are lined up. So 2x minus 3y equals negative 12. And now I need to decide, should I add or subtract these equations to eliminate the y variable? Since the coefficients are the same absolute value but opposite sign, adding will eliminate the variable. If I tried to subtract, if I did 3y minus negative 3y, that'd be 6y, it wouldn't eliminate it. But in this case, when I add the two equations, so when I add the like terms in the columns, 12x plus 2x is 14x, 3y plus negative 3y is 0y, the y is eliminated, and 96 plus negative 12 is 84. Divide the coefficient of 14 to the other side, 84 divided by 14 is 6. And then I just need to sub my answer of x equals 6 into either of the original equations. We could sub it into here, or either of the ones with the fractions eliminated, or this one that's been tripled. Any of those equations are going to result in the same answer for y, as long as we've solved for x properly. So I'm going to sub my value of 6 for x, I'm going to sub it into this equation right here. I'm going to sub it into equation 2 that's been multiplied by 6. So I'm going to sub into a version of equation 2. So I'm going to use the version that was 2x minus 3y equals negative 12. I'll sub my answer of 6 in. And I've got 2 times 6 is 12. I'll bring this negative 12 over, becomes positive 12. And I'll move this negative 3y to the right, makes it positive 3y. So I have 24 equals 3y. Divide the 3 to the other side. 24 over 3 is 8. So my solution is x equals 6. Y equals 8. Graphically speaking, if we were to graph both lines, they would intersect at the point 6, 8. Let's do our last example. There are no decimals or fractions to deal with. The equations are of the proper format, x and y on the left, the constant on the right. Now we just have to make the coefficients of either the x's or the y's have the same absolute value. So let's make the x's both have a coefficient of 10. But something unique is going to happen with this one. To make the x in equation 1 have a coefficient of 10, just like equation 2, I'm going to need to multiply it by 2. So 2 times equation number 1 will give me 10x plus 4y equals 4. Notice all three terms got multiplied by 2. Equation number 2 can stay as it is because its x already has a coefficient of 10. Notice when we made the x's get the same coefficient, the y's also ended up getting the same coefficient. So let's see what happens in this scenario. Let's still focus on the terms with an x. Let's try and eliminate the x. Since their coefficients are the same absolute value with the same sign, subtracting will eliminate. Now let's subtract all the like terms in each column. So 10x minus 10x is 0x, which means the x's are eliminated. 4y minus 4y is also 0y, so we've got 0y as well. But 4 minus negative 4, well, that means 4 plus 4, which is 8. 0x plus 0y equals 8. Well, that's just 0 equals 8. And that's clearly not true. 0 does not equal 8. So what does this tell us? This tells us that the lines must be parallel and distinct. It means there are no solutions to this system. So we would say there are no solutions. The lines are parallel and distinct. So that's all the examples I'm going to go through with you. Before I close up this video, I did tell you that at the end I would talk to you about algebraically why we are allowed to just add or subtract two equations together. Looking back at example 1, we wrote the two equations on top of each other and we decided to add them, and that would eliminate the y variable. But why are we allowed to do that? Algebraically, why does that make sense? Really what's happening is we are using the balance method. Let me just move this down a little bit and remind you the balance method is the method that tells you that you can do whatever you want to an equation as long as you do the same thing to both sides. Then it keeps it balanced. Right? If I were to rewrite equation 1, 3x plus 2y equals 19. To try and solve this algebraically, you can do whatever you want as long as you do it to both sides. If I thought subtracting 12 from the left side would help me solve this equation, I could do it as long as I also subtracted 12 from the other side. Maybe you thought adding 5 would help you solve this equation. We could do it as long as we added 5 to both sides of the equation. And actually, adding 5 does help solve this. Let me show you how. I've got 3x plus 2y, and if I add 5, well actually, instead of 5, notice what does equation 2 tell me about 5? It tells me 5 is equivalent to 5x minus 2y. So instead of writing 5 on the left, I'm going to write something that's equivalent to it. 5x minus 2y. And on the right, I'll just leave it as a 5 because that'll collect nicely with my 19. So notice, what did I do? I just added 5 to both sides. And I know that 5 is equivalent to 5x minus 2y, so I changed the 5 on the left to 5x minus 2y. How does that help? Notice when I collect the terms on the left side of this equation, 2y minus 2y, the y's are gone. And what I'm left with is 3x plus 5x, which is 8x, equals 24. And now we are at this line right here, 8x equals 24. The method of elimination is just an organized way of doing this balance method. You just line them up, the like terms, in columns to help you with the collecting more easily. But it still has the algebraic foundation of using the balance method to solve the equation. So hopefully that helps you get an idea of why we're allowed to just line up the like terms and add them in this way. So that's the end of the lesson. Make sure you give some of the practice questions a try.